All right, welcome to Unit 11. It's actually Chapter 16 in our book, Electrostatic Forces and Charges. So we're going to talk about static charges and the forces they apply. Great news, all of the kinematics we've used before can be used again to help us with if things are moving and accelerating, if there's constant acceleration equations or problems. We also have the free body diagrams, everyone's favorite. Yay, free body diagrams. Don't worry, they're not going to get too crazy, but we will have some free body diagrams because these are forces, and forces can be put and simplified on our free body diagrams to help us understand the situation. So we will be dealing with vectors, of course, and vector addition still, having to split the vectors into their components, and so that's what we're going to be doing with this, and it's really not that bad, and I think it'll be an enjoyable unit for us. Okay, so the first problem we have, and I'm going to use the first problem kind of to discuss things too, so I'm going to meander a little bit. Mr. Intershot, you always meander. Well, the journey. Life's about the journey, right? Not just getting to the end. It's enjoying the parts in between. So we're going to first talk about review. Like charges, what do? Like charges repel. Whoops, repel. Opposite charges or opposites attract, right? Opposite charges attract. Okay, just remember that. Basic rules for static charges. Opposites attract, like charges repel. So remember that for free body diagrams. And a lot of these too. What I would suggest is draw your free body diagram and look at the charges real closely. When you fill into Coulombs Law, which we'll talk about in here in a second, don't worry about charges because you've already decided on the direction. Okay, so let me draw two charges. One is negative and the other is positive. So we have a charge is located this many meters from that. It doesn't tell us which side, which is important, but they say what is only the magnitude. So they don't want the direction. Remember, vectors have two components to them, a magnitude, a size, and a direction, which if it's just 2D, you can put a negative or a positive. If it's 1D, you can put a negative or positive. If it's 2D, you got to use degrees from a reference point. But anyway, so we'll just draw the negative. In this case, it doesn't matter which side you put which one. So we're going to have the negative charge here, and that charge is 2.87 times 10 to the negative 9th coulombs. Okay, we have a positive charge here. All right. And that positive charge we're going to call 4.73 times 10 to the negative 9th coulombs. Coulombs is our unit of measurement for charge. Here's our distance. Maybe I should have done that in a different color. We'll maybe put it in black. Our distance apart is 3.32 meters. That's important to have it in meters, important to have it in coulombs. Let me say that again. Important to have things in coulombs, important to have things in meters. So what is charge? We'll call this charge A and this charge B. I know it doesn't say that, but this is just, I'm also discussing this in general, not just this problem. What is the force, what is A doing to B? So basically think of A as stationary, they're both stationary, but what is A doing to B? And they're opposites, so it's pulling it. So I would say A is exerting this direction of a force on B because they're opposites. Well, what is B doing to A? B is pulling A in this direction because isn't it pulling? So if we were doing a free body diagram and we were concerned with A, we'd have this there, and that's it. And if we had a free body diagram on B, if we were wondering what B was doing, that's the free body on B. Obviously, there's no, it's unbalanced, so there would be causing acceleration, but we're just going to call them stationary right now, so we're not worrying about the motion. There is no motion parts to this question. So, but that's important to know. Where's our frame of reference? What are we concerned with? Are we concerned with A? Then what's B doing today? If we're concerned with B, what's A doing to B? And you use these rules here, and then you decide which one, you pick which one you're worried about, and then you draw the diagram. What is the other one doing to the one we're concerned with? Okay, on to Coulombs Law. So Coulombs Law is F equals this constant, I'll call it K subscript C, and so then we have Q1 times Q2 over R squared, where R is a distance between them. Q is the charge in coulombs. This is in meters. Charge in coulombs. Q2, same up here, but the charge, I shouldn't say same, charge on the second one, charge on 2, and that, and Kc, this is important, Kc is a constant. It is a constant, and it is always 8.99 times 10 to the 9th, and its units here, newtons times meters squared over coulombs squared. This means that you better have, your force will be spit out in newtons, and you better have your distance units between them in meters and your charge units in coulombs. And this will all cancel out and work out so that it spits newtons out on the force, which is what we would hope and expect. So that's what that is. That's Coulombs law. It looks very much like Newton's gravitational law, right? You know, where this was a G, and this was M1 and M2, and this was the distance between the two objects and finding the gravitational force of the two objects on each other. So it's pretty awesome that those are the same. Now, the constant's different, but the equation's the same. Pretty cool. I could put it over here just so you can see it for comparison contrast. In the force, the gravitational force is equal to this G constant, M1, M2 over distance squared, and R is this distance squared. It's very much the same, except for this constant, right? Pretty cool how nature works that way. Pretty awesome. And so let's get to the problem and fill in and see where we sit with this. So once again, when we fill into Coulombs law, I kind of want you to ignore the charge, the sign on the charge, and then you decide and put the charge on it in your free body diagram. This problem actually doesn't require it, but the next problem we will be mindful of the direction, because magnitude just wants the size of this. So this is 8.99 times 10 to the 9th. All my units play nice, so I'm going to leave them off because I'm kind of fighting for space here, and it's gonna be a little brutal here. Yes, this should be a negative, but I said leave them off when filling into Coulombs law for now. So we're multiplying there, and we're going to multiply by one more. Okay, they're all in coulombs, and you can divide the whole thing by the distance squared, which is 3.32 squared. Okay, so now what does that get us? This gets us an F equal to, I have my numbers here somewhere. Oh boy, oh boy, oh boy, oh boy. It is 1.10, oh, it's up there, I should have done. 1.1072 times 10 to the negative 8 newtons. Now, I would normally say we got to figure out the direction, but we don't need that here. I'll go over it here. I mean, if you wanted, the force of this on this would be to pull it in this direction, right? Let me get a different color, right? So if we're worried about this one's being pulled this way, so it would be a positive force, but this one on top of this one, force pairs again, guys, Newton's third law, force pairs, this would be, if we're worried about a free body diagram on this one, it would be this one be pulling this one this way. So it'd be a negative force because that would be denoting the direction in the negative x direction. So that's how it would be. But this is your answer, straight up, because it only wanted magnitude, and I said this was arbitrary anyways. We could put the either side we want. So give that a shot. Give it a try. Let me know how it goes.